We're continuing our discussion of section 2.4 and right triangle trigonometry. I'll note that we skipped over a lot of the material in section 2.4 in material recording involving parallel and perpendicular lines and other things we'll come back to at a later time in this course. Now we're going to move into right triangle trigonometry, and a lot of people get the idea that right triangle trigonometry is somehow this mysterious thing that involves the letters SIN or COS or TAN and somehow associates them with angles and other mysterious objects. I think people get the wrong impression. Right triangles all share properties that make them really important for us, and so we use them as a tool to help us understand some of the physical world around us. And so understanding something about right triangles can help us do that. Now, among some of the properties that make them important is that the ratios of right triangles among similar figures is always the same. What do we mean by similar figures? A similar figure in a right triangle sense is a figure that contains all of the same angles. So for example, we might say in geometry that angle 1 here is equal to this angle 1. Angle 2 is therefore equal to this angle 2. And of course, both of these contain right angles here at the appropriate places, right angles being 90 degrees. And so in this case, we should say that the ratios of the sides are always equal. We don't even need any fancy trigonometry to tell us how to deal with this, because we know that if it's true that the two figures are similar to each other, that the ratios of their sides will be equivalent as well. So for example, let's say we're interested in finding the length of side x right here in this triangle. Given that this first triangle, the large one, is similar to the small triangle right here. Well, what must happen? That means that if we were to take the ratio of this length x to this length 39, it would be exactly the same as the ratio of that side 12 on the smaller triangle to its longest side 13 in the smaller triangle. Well, that's not a bad one to solve at all. Hopefully most of us have sort of an idea of how this is going to work. What's going to happen right here is that we have essentially a fractional equation that we can solve by multiplying both sides by 39. 39 times what's on the left, 39 times what's on the right. We can think of it as 39 times over 1 if we'd like. 39 divided by 39, that cancels out. That just gives us x. Of course, 13 goes into 39. We know exactly 3 times. And so we take 12 times 3, and that gives us our answer right here of 36. So this length must be 36 in order for these ratios of these sides to be exactly alike. Now we can say the same thing about the length of side y divided by, come on, pen, stop doing that to me, y divided by the length of the hypotenuse, in this case 39, is equal to 5. The length of this side right over here divided by its longest side, 13. These two ratios must be alike. Right? So we know that if we multiplied both sides by 39 again, in order to make that work out, write this out right here, we know that the 39s divide out on the left, isolating y. On the right, 39 divides by 13 3 times, and 5 times 3 is 15. And so we know that that would be the length of this side over here. Y equals 15 there. So this is how we might handle the similar triangle problem. So you're asking yourself, well, this is all algebra. How does this help me in dealing with trigonometry? Well, I'm just getting to that. It turns out that those ratios are highly important when it comes to the length of the sides. The ratios themselves are what define what we call our trigonometric ratios, and there are 6 of them that you must know in this course. The first 3 are the most important ones in that these are the ones that we always remember from earlier trigonometry classes and are the ones that appear on calculators and other devices. We define the sine of an angle to be the ratio of the opposite length to the hypotenuse length of that right triangle. It's interesting to note that for that angle, regardless of how big or small the triangle is, the ratio of the opposite to the hypotenuse side will always be the same, as we illustrated in our last example when we took y over 39 and set it equal to 5 over 13. Cosine of an angle is the ratio of the adjacent side divided by the length of the hypotenuse side. Again, we used that when we were solving for our length x in our similar triangle problem. So you can see that, in fact, if I go back a slide right here, let's get rid of that thing right here. If we go back, we can see, in fact, that our ratio right here was for, let's call this angle, I'll use the Greek letter theta. We call this angle theta right here. We could say that our ratio right here of cosine of that angle is the ratio 15, not 15, I'm reading the wrong side again. Good job, Professor Peoples. 36 divided by 39 is our adjacent side and our hypotenuse side, but when we reduce that, we find that that's exactly the same as 12/13. Right? So it doesn't matter how big that triangle is, this ratio for cosine is always the same. And we could have said the same thing for our sine ratio. Right? Since this angle is the same, the sine of our angle theta is the ratio of the opposite side to its hypotenuse side. In this case, that would have been 5 over 13. But even if we took it from the larger triangle and took 15 over 39, we would still reduce to the ratio 5 over 13. So this ratio becomes a constant for every triangle that right triangle that contains that particular angle theta. We have 4 others that we define. We define the tangent of an angle being the length of the opposite side over its adjacent side. And then 3 others that we don't normally see, but we use them all the time. They are reciprocals of the others. For example, cosecant of an angle is the ratio of the hypotenuse to the opposite side of the right triangle. You see that that is actually the reciprocal of our opposite over hypotenuse, which was sine. So sometimes we do express this as being 1 over the sine of the angle theta. Our secant is the ratio of the hypotenuse to the adjacent side of the right triangle that contains that angle. Hypotenuse and adjacent came up before when it was cosine in the form of adjacent over hypotenuse, and so we often express this as 1 over the cosine of the angle. And of course, cotangent is the ratio of the adjacent side to the opposite side of the right triangle containing that angle. We saw opposite and adjacent in the form of tangent before. So, as we did before, we could express this as 1 over the tangent of the angle theta. And we'll go over some examples in our next portion.